Okay. Thank you. Thank you very much for introducing me. And thank you very much for giving me opportunity to make presentation here. So Abel, you can listen to me?
Yes. Perfect.
Okay. Yeah. So I will start my talk. Last 1 year ago, I don't know how to connect to Zoom, so I was very big trouble. But thanks for the, support by the committee, organization, we can connect to the Zoom finally. So thank you very much. Okay. So I will talk about the two compounds, about the chromium ion compound and the cesium copper chloride. So we briefly introduce this compound and go to the experimental section. So firstly, the chiral magnet has very large attention due to the unique magnetic structure, such as Chloride lattice and the chiral magnetic soliton lattice, and the applied magnetic field. So the applied field exhibits the very unique magnetic structure. This is the interesting point about the chiral magnetic compound. So one typical example is the chromium niobium compound. So this crystal structure is chiral belonging to the space group of P6322. And it also reported that it's forming the chiral magnetic structure with the period of the 500 angstroms. So firstly, this compound was reported as a ferromagnetic compound in 1980s, but after the detailed, precise measurement, experimental measurement showing that it cannot be ferro, but forming the long periodic chiral ferromagnetic structure. This is an interesting point. So it also shows the unique magnetization process described by the chiral magnetic soliton lattice based on the Sine-Gordon equation. So recently this magnetic structure is proved by the Lorentz microscopy. So the left figure showed showed the Lorentz result of the Lorentz microscopy. This period increasing period can be changed by the amplitude of the applied magnetic field. This period is well fitted by the formation of the chiral soliton lattice. So this period affects the magnetic properties such as the magnetic resistivity and so on. So this is why this compound is very, very interesting. So as for the second compound is the cesium copper chloride. This compound also forming the chiral crystal structure belonging to P6122 or P6522. It was reported that it can form the chiral ferromagnetic structure, but it was very difficult to validate whether this is chiral ferromagnet or not, because it was very difficult to grow the homochiral single crystal. In case of normal crystallization technique, single crystal specimen includes right-handed and left-handed chiral crystal domains by 150-50. So in this case, it was very difficult to investigate this kind of work experimentally. But recently, we successfully grew the enantiochia single crystal over 1 centimeter length, and successfully proved by the chiral ferromagnet by the Polar's neutron diffraction. So another interesting point of this compound is that the propagation vector, because the propagation vector is one-third vector. This means that this compound forming the chiral ferromagnet along C-axis and it forming the triangular antiferromagnet in AB axis. This means that along C, this is the ferromagnet, but in in AB, it can be a kind of frustrated state. So that, and also the spin is 1/2, so that it can be the very interesting point. So today we will go to the experimental result of the two compounds. First one is chromium ion sulfide. So as I talked before, this is reported that it can form the chiral magnetic soliton by the Lorentz microscopy. But it was very difficult to try the neutron diffraction because the size of the single crystal is very, very small. So to try the neutron diffraction technique in this compound, we grow at least 100 pieces of the single crystal, and we find the orientation of the crystal and put in the aluminum plate. So in total, 50 milligrams of the single crystal can be put in a plate. So that with this crystal plate, we try the small angular neutron diffraction. So we briefly, because of the problem that time, so we briefly explain show the result. So that this is the field dependence of the propagation vector when we apply the field along perpendicular to the c-axis. So the satellite peak position decrease with increasing the magnetic field. So that this behavior is very well fitted by the theoretical calculation by the formation of CSL. This means that it can be the very good evidence about for the formation of chiral soliton lattice in this compound. So the next topic is the cesium kappa chloride. As I talked before, in this compound, magnetic moment have the couple. This means that couple has a 1/2 spin. This means that it formed the triangular antiferromagnet structure in AB plane. This means that it can be very interesting point about as a frustrated magnet. So it is theoretically reported that when we apply the field along c-axis in this compound, it formed a variety of magnet structure. So the umbrella, coplanar, and up, down. So basically, in total 5 structures. So the experimentally, in 1970, it is reported that it can form the umbrella and the 2-1 coplanar, only 2 phases. So the no how to say, Y phase and so on. But recently, we tried magnetization measurement with pressure, high pressure. In that case, we observed a new magnetic phase, so as the Y phase and up, down phase, maybe up, down phase. At least it is clear that when we put the pressure around the 0.7 ZPa, magnetization once saturated around 1/3 mV per copper. This means that it expects the, up, down magnetic structure. And before go to the up, down phase, it shows the, very small slopes. It may be the Y phase. At least we can say that we can observe the up, down phase around 0.7 GPa. So here we would like to report the neutron diffraction result of this compound with magnetic field and high pressure. So as we go back to the introduction, so the magnetization process, we can expect the umbrella phase are below the 13 Tesla, and around 13, it can be up, down, and finally, go to the 2-1 coplanar phase. So that in that case, the magnetic propagation can be described 1/3 Q, and then in case of up, down, 1/3 O, and finally go to the 1/3 O and 1/3 delta. Based on the theoretical calculation by the Nikni model, so the Hosoi recently recalculated this model, and they found that, applying pressure, it changes the lattice parameter, and changes the ratio of the lattice parameter in A and C, and it affects the exchange interaction between AB and C. So that in that case, the applied pressure induces two more magnetic phases. Without pressure, it only have the two phases at umbrella phase and 2-1 coplanar phase. But with applying pressure, it shows the up, down phase and the Y phase between the conventional two phases. At least this result, at least the appearance of the up, down phase is very consistent with the magnetization result. And we may observe the Y phase when we apply the pressure, but at least when we apply the pressure around 0.8 ZPa, we can see small slope between the up, down phase and the umbrella phase. So that here, in case of the right figure, we see the area by the dotted circle. So that we may observe the, Y phases in the neutron diffraction. So that we also estimate the, intensity of the each phases. So that in case of the, just checking the field dependence of the intensity, we can distinguish the three phases. In case of Y phase and the 2-1 coplanar phase, the magnetic structure can be described by the three propagation. Yeah. Okay. So, and in case of up or down phase, it can be described as only 1/3 O. So the experiment were performed at the E4 at 8 GeV in Germany. And we prepared a single crystal of the cesium copper chloride. Yes. And we shaped the crystal so as to put in the pressure cell. So the size of the single crystal is very small. So the signal is also small, so small. At least we tried the measurement. Experimental condition is showing like this. At least we tried the pressure around 0.3, 0.65, 0.7. We want to observe the pressure around 0.8, but it was very difficult. Probably caused by the pressure cell, problem of the pressure cell, so the highest pressure was 0.7 GPa. We may see Y phase in highest pressure. So the result is next. So the first 0.3 GPa, so that it is very consistent with the conventional result, because in this pressure, magnetization also shows the only two phases, umbrella and two coplanar. So that this result is very consistent with the previous result. So that when we apply the pressure around 0.65 GPa, we successfully observed the up, down phases. So that in case of the around 13 Tesla, so that we magnetic peak only observed at 1/3. Oh, this is a very important point. But in this figure, there is three, data in a graph, so that we normalize the, intensity of the 1/3 O between 13 Tesla and 14.2 Tesla. So that in that case, we can apparently see the, satellite peak at 14 Tesla, but in case of 13, we see only single peak it is very good evidence about the formation of the up-down magnetic structure. So next is slightly more pressure, but unfortunately the data looks very same with the pressure at 0.65 GPa. So at the present moment, it is difficult to prove that this compound have the Y phase using the neutron diffraction technique. But as we see the, dependence of the field dependence of the magnetic diffraction intensity, behavior is a bit different between 0.56 GPa and 0.70 GPa. So in case with 0.65, so that when we change the umbrella to up down, we see once it changes the we observe the peak around 1/3 O, it monotonously decreases with increasing the field. But in case of 0.70, when we observe the satellite a peak at 1/3 O, it increasing with the increasing field and then slightly flat in the very small region and then decrease. So that it may be one evidence that it may form in the, Y phase. But reasons why that we did not observe the magnetic satellite peak in this area, maybe the, very, very small signal because in this experiment, the size of the single crystal is very small. So the background intensity is also very large. So that for that case, it may fail to observe the very tiny, very small magnetic signals. Satellite signals. So the summary is like that. In case of the neobium, chromium neobium compound, we successfully observed the chiral magnetic soliton. And in case of cesium copper chloride with high pressure, for that case, we observed the up-down magnetic structure. That's all. Thank you.
Thank you very much, Kousaka-san, for this nice experimental talk. Then